Hello everyone, welcome to lecture 20 of the course Diffusion in Solids. So today's lecture is a tutorial lecture as we have done all week, previous weeks also. We'll be covering some problems on atomic mechanisms, correlation factor and temperature and pressure dependence of diffusion. So like I always say, please try the problems yourself first and then play the videos to look at the solution. So let us start our question 1. So consider the following cases. Diffusion coefficient of carbon in alpha iron at 773 Kelvin is designated as D1. Diffusion coefficient of chromium in alpha iron at 773 Kelvin is D2. Diffusion coefficient of carbon in alpha iron at 973 Kelvin is D3 and diffusion coefficient of chromium in alpha iron at 973 Kelvin is D4. Now, you have to identify the correct relation or relations and you have to look each of them carefully and see if what is correct. So, what is the difference basically between the carbon diffusion in alpha iron and the chromium diffusion in alpha iron? So, as you may be aware, carbon in alpha iron is a interstitial solute. It occupies the interstitial positions, whereas chromium in alpha iron, which is having a similar atomic radius, it is a substitutional solute. So, therefore, the carbon diffuses by interstitial mechanism and chromium diffuses by substitutional mechanism. And we have seen that interstitial mechanism, the activation energy comprises only of the migration term, whereas here in the substitutional case where the diffusion is by vacancy mechanism, the activation energy also has a term of delta HV, which is the vacancy formation energy. So, the interstitial solutes diffuse at much faster rate than the substitutional solutes. Therefore, the correct options are B and C. Why? Again you can see carbon diffuses faster in alpha iron at a given temperature. So, if you see the option B, which is D1 by D2, that means this is the chromium diffusion D2 and carbon diffusion is D1. So, D1 is higher than D2 and therefore, you have D1 by D2 is greater than 1. But there is another comparison also. Please remember, do not forget that about the temperature. So, if you see this relation D2 by D4 for example. So, chromium in alpha iron at 773 and 973. So, we know that diffusion coefficient increases with increase in temperature and therefore, D2 is lower than D4 and hence the relation C is also correct, which is D2 by D4 is less than 1. And this relation D1 by D3 is greater than 1 is not correct because D1 is at lower temperature. So, the D1 by D3 actually should be less than 1. Moving on to the second question. Which of the following statements are true about the monovacancy and divacancy concentration in metals? So, monovacancy concentration is less than divacancy at all temperatures, or divacancy concentrations are less than monovacancies at all temperatures, and divacancy is greater than monovacancies at relatively high temperatures, or divacancy concentration is greater than monovacancy at relatively low temperatures. So, this is more or less a straightforward question. We have seen this graph, the log of concentration versus 1 over temperature, and we see that the divacancy concentration dominates at the higher temperature. Remember, it is a T inverse plot. So, these are the regimes of higher temperatures. So, therefore, the correct answer is C. The third question is, a small amount of nickel 0.005 mole fraction is added to pure copper. Determine the ratio of unpaired vacancies in dilute copper nickel to that present in pure copper. Now, here You remember that this was the equation we saw where we were talking about the vacancy concentration in dilute alloys. So, this is a small amount of nickel. So, this is a dilute alloy, and the vacancy concentration is given by 1 minus ZXB into exponential minus delta G F of mono vacancy formation divided by KT plus ZXB exponential minus delta G of F by KT for the B. So, where Z is the coordination number and XB is the solute fraction. Now, here the first term, actually this first term is the concentration of unpaired vacancies, and this is reduced by a factor 1 minus ZXB relative to the solvent. So, if this was alone, you remember that without this fraction, this term alone represents the vacancy concentration in pure A. Now, because there is 1 minus ZXB factor coming due to the solute, so therefore, that much concentration is reduced. So, therefore, the ratio of the unpaired vacancies in dilute copper nickel to that present in pure copper will be given as 1 minus ZXB, which comes out to be, if you put XB as 0.005 and FCC Z is equal to 12. So, the ratio is 0.94. Question number 4. What are the limitations of differential dilatometry method that is used to determine the vacancy concentration in metals? So, we studied that there are a couple of methods. One of them is differential dilatometry, another is positron annihilation, which are used to determine the vacancy concentration in metals. So, here you might recollect. So, here in differential dilatometry, what you need to do is you need to measure the change in the lattice parameter as well as change in the length, and the difference of that actually gives you the vacancy concentration by multiplying by appropriate factors. So, what are the limitations? So, the first one is high precision measurements of change in length and lattice parameter is needed. That is correct. This is a limitation because in differential dilatometry already the vacancy concentration are in range of 10 power minus 4, and the lattice parameter or the change in length are of very small order. So, you require a high precision measurements of these changes if you want to measure the vacancy concentration correctly. The second option is it can be only used up to room temperature. This is wrong. This is not the case. It can be used up to higher temperatures also. The third is measurements are difficult for non-cubic structures. Yes, because we usually multiply by a factor of 3 when we want to convert to the volume expansion and so on. But in the non-cubic structure, because the expansion is not uniform in all directions, so therefore, the measurements become difficult. Then simultaneous measurements of length and lattice parameter changes at a particular temperature are needed. This is again correct. This is a limitation because it is not always possible to measure them simultaneously. So, typically these are the separate experiments done trying to maintain the same range of temperature and trying to see that we measure at similar temperatures, but you cannot measure these things in one experiment. So, you do separate, but so this is a certain limitation that is there for this method. So, this the correct option then is A, C and D. Moving on to the next question. Which of the following diffusion mechanisms in binary alloys lost their validity once Kirkendall effect was established? So, the options are direct exchange mechanism, interstitial mechanism, interstitialcy mechanism and ring mechanism. So, if you see the direct exchange mechanism and the ring mechanism, they are illustrated here. Direct exchange means that the tracer basically exchanges its position directly with the neighboring matrix atom. And in the ring mechanism, this happens in a cyclic way. But in both these cases, you see that if the tracer atom and the matrix atom, let us say in direct exchange, have to exchange their positions, that means they both should diffuse at the same rate. So, if you extend it to alloys, that means A and B constituents in a binary alloy should diffuse at the same rate. But Kirkendall effect showed that that is not the case. The movement of markers actually demonstrated that the movement is not, the diffusion rates are not uniform, and therefore, this is not valid anymore. So, the direct exchange and the ring mechanisms are not valid. We will see about Kirkendall effect in more detail in the upcoming week. So, there you can study more about this, that what is meant by this unequal diffusivities and how Kirkendall experiments were designed and so on. So, in this case the correct answers are A and D. Question number 6, select the most appropriate statements about the interstitial C mechanism. So, interstitial C mechanism, the statement 1 is formation enthalpy is usually higher than vacancy formation enthalpy in metals. This is correct because here the atom has to sit in its own interstitial site. So, which puts a lot of strain on the neighboring atoms. So, the formation enthalpy is usually much higher. The formation enthalpy is usually lower than, so since A is correct, of course, B is wrong. The mechanism is more relevant in metals for the case of radiation induced diffusion. This is correct because as I said that for the self interstitials or interstitial C mechanism, the delta H is almost 2-3 times that of vacancy formation. So, the concentration of vacancies are much higher. But when there is a radiation induced diffusion, that means the radiations are bombarding your crystal, then the atoms are ejected out of their lattice position and then they sit on their own interstitial sites. So, that is where it is more relevant. The mechanism is more relevant for diffusion in semiconductors. This is also true with the relatively open structures. The interstitial self-interstitial formation is relatively easier in the semiconductors. So, we will see when we talk about the semiconductor diffusion in the later weeks. So, the correct answers are A, B and D. So, the next is if delta HF and delta HM represent the formation and migration enthalpy of defects, then which of the following relations are true for dilute alloys. Okay. So, the first is the delta HF formation is not equal to 0 and delta HM is not equal to 0 for interstitial mechanism. This is false because interstitial sites are actually present everywhere. So, you do not need any formation energy to create the interstitial sites. So, therefore, for interstitial mechanism you have delta HF as 0 and there is a certain migration enthalpy that is associated. So, out of A and B, correct option is B. Then third is delta HF is not equal to 0 and delta HM is not equal to 0 for interstitial C mechanism. This is correct because you need the atom to be ejected to the interstitial sites, its own interstitial site, which requires a certain energy. Hence, in fact, we saw that this energy is more than the vacancy formation energy also. So, therefore, the correct option is C in this case. So, here it is wrongly written, it should be B and C. So, moving ahead, identify the diffusion mechanism showed in the image below. So, you see here this is an interstitial solute and with the sequence of jumps finally it ejects, or in other words kicks out this matrix atom into its own interstitial site. So, this is where, and then later this tracer atom will diffuse again to interstitial actually. So, this right now behaves as interstitial solute when it is in this position. Here it behaves as a substitution solute when it is this position. So, basically this can occupy both interstitials as well as the substitutional sites. Therefore, this is an interstitial substitutional mechanism, and out of that it is what is known as kick out mechanism. So, where this is basically kicking out one atom from the matrix to its own interstitial. Question number 9 is a derivation which tells dB is equal to 1 by 6 gamma b alpha square. Please excuse me for this notation. This is in the lecture slides, this was written as capital gamma, but I think it does not make much difference to the understanding, but please remember that these are the same quantities. So, how do we do that? We derived it, remember, for the simple cubic lattice. So, we had one plane and another plane, let us say the concentration of atoms in the plane 1 is N1 and it is N2 in the plane 2. So, the number of atoms are like that, and the jump frequency in the forward direction it is gamma plus, in the backward direction it is gamma minus. So, the total flux will be J plus minus J minus, that is forward minus backward. So, the forward flux is nothing but N1 into gamma in forward direction, that means how many number of atoms are there multiplied by the jump frequency in the forward direction, minus N2 into jump frequency in the backward direction. So, then N can be also written as Ni plus dN by dx into alpha by 2. Similarly, it can also be written as N2 minus dN by dx into alpha by 2. So, N is basically number of atoms at any given x. For simple cubic lattice, we had assumed a linear atomic movement. However, in case of FCC, jumps at different angles contribute to the diffusion in x direction. So, this is the important difference because in simple cubic we had considered only diffusion in one dimension, the linear movement, but here even if you have to consider diffusion in x direction, it can have jumps which are coming at an angle, and then so therefore, alpha has to be replaced by alpha cos theta. So, the projected length along the x axis has to be taken. So, therefore, N1 is equal to C alpha cos theta I minus alpha square cos square theta I by 2 into dC by dx. Similarly, N2 will be equal to C alpha cos theta I plus alpha square cos square theta I by 2 into dC by dx. Okay. So, alpha we are replacing by alpha cos theta. Now, therefore, the flux can be written as we substitute this values of N1 and N2 here, and we can write the flux as C alpha cos theta I minus alpha square cos square theta I by 2 dC by dx into gamma plus minus this term into gamma minus. So, if you see that these two terms will cancel out, and if you rearrange a little bit, then you get minus alpha square by 2 cos square theta I into gamma plus plus gamma minus plus C alpha cos theta I gamma plus minus gamma minus. Now, therefore, the Jp can be written as an index I. So, this is equal to 1 by 2 alpha square gamma b by z into summation I equal to 1 to z cos square theta I dc by dx, because I to z takes care of the different directions in which this jump can happen. So, for FCC Z is equal to actually 12. So, therefore, if we consider 1-1-1 plane for example, within the plane there are 6 neighbors in hexagonal arrangement. So, you can see that there are 6 neighbors, and then there are 3 on the top and 3 on the bottom. So, outside the plane and below the plane, above and below. So, the jump factors, basically cos square theta I is nothing but the angle between the different jump factors. So, depending upon the type of jump, so here we have marked the different sites. So, 1, 2, then there are 3 sites that are marked 4 and 5. So, depending upon the vectors, depending on the angle they make with the diffusion direction. So, if the diffusion direction we take as x, then you can see that for site 1, the theta I will be 0. So, cos theta I will be 1 and cos square theta I will be 1. For position 2, you have it is in the opposite direction. So, it is -1, but cos square theta I is again 1. For the position 3, then there are 4 such possible sites where the angle is 60 degree. Accordingly, you take the cos square theta I. There are such 4 jump vectors. For the position 4, again there are 4 jump vectors and the angle is 120 degrees, and for the position 5 there are 2 jump vectors which are perpendicular. So, then you take the average of these cos square theta I, and you get 1 into 1 plus 1 into 1 plus 4 into 0.25 plus 4 into 0.25 plus 0 into 2, which comes out as 12, which comes out as 4, which can be written as 12 by 3. 12 is nothing but the coordination number, so you can write it as z by 3. So, if you substitute this here, the values, then what you get is Jp is equal to 1 by 2 alpha square gamma b by 12. This can be replaced by 4 into dc by dx, and here this is 1 by 6 alpha square gamma b dc by dx. So, if you compare it with the Fick's first law, then you can write dB is equal to 1 by 6 alpha square gamma b. So, I will just add minus here which was missing earlier. So, this way you can show that this is true for FCC lattice also. So, this relation holds good for the cubic lattices. Moving on to the next question, assume a hypothetical one-dimensional lattice with linear chain of atoms. What will be the correlation factor for diffusion of tracer atom by vacancy mechanism? So, here if you see, we say that f is equal to 1 minus 2 by z. Since z is equal to 2, therefore, f will be equal to 0. So, we can illustrate, suppose this is a linear chain of atoms. For simplicity, I have just put 4 atoms. This is a tracer atom and a vacancy. Now, let us say it exchanges its position. So, now the vacancy will come here and the tracer atom will come here. Now, because it is linear chain and it cannot move in any other direction, so immediately it goes to the vacancy which is next to it, which is in the reverse direction. So, it will keep on doing like that. So, therefore, you have a no net displacement, the correlation factor comes out to be 0. Question number 11. For the sequence AS, AI and AS in the interstitial C mechanism, the value of average of cos theta is. So, this we have seen that in the interstitial C mechanism, when tracer is in the interstitial site, it can move in any random direction, but when it is in substitutional site, then it has the correlation effects, it has the jump probabilities which are unequal, and therefore, in this particular sequence, AS, AI and AS, the average of cos theta is 0. So, the correct answer is C in this case. Question number 12. If C1 represents the average of cosine of angles between I plus 1th and I plus 2 jumps, C2 represents the average of cosines of angle between I plus 1th and I plus 4th jumps, what will be the relation between C1 and C2? So, here we are given that cos theta I plus 1 comma I plus 2 is C1, cos theta I plus 1 I plus 4 is equal to C2. Let us substitute I plus 1 as k. So, essentially what it means is that average of cos theta k plus 1 is C1 and average of cos theta k plus 3 is C2. And we have seen that cos theta k plus 3 can be written as cos theta k plus 1 to the power 3. So, this was the relation we already showed for the cubic lattice, that cos theta I plus j, average of that can be written as average of cos theta I plus 1 to the power j. So, therefore, C2 will be equal to C1 cube. Now, coming to the question number 13, by Manning it was shown that the escape probability for solute diffusion is given by this expression. It is a function of alpha, where alpha is omega 4 by omega. Now, what will be the value of escape probability when omega 4 is equal to omega? And what will be the approximate value of correlation factor if vacancy solute exchange is much slower than the vacancy solvent exchanges? So, for the part A, it is very straightforward that omega 4 equal to omega means alpha is equal to 1. So, if you put here this equation, then you will end up in this solving this equation, and you get F3 is equal to 0.736. For the FCC structure, we saw that solute correlation factor can be approximated as 2 omega 1 plus 7 omega 3 by 2 divided by omega 2 plus 2 omega 1 plus 7 omega 3 by 2. Where remember that omega 2 refers to the vacancy solute exchange. So, if that is slow, that means omega 2 is very less than compared to omega 1 and omega 3. So, if you neglect this omega 2 in comparison to this factor, then you have F for solute is approximately equal to 1. And we come to the last question of the tutorial. Refer to this data and calculate the activation energy Q, frequency factor D naught, and the activation volume. So, what essentially are given is at a given pressure, the variation of diffusion coefficient with temperature, and T is equal to 800 Kelvin, the variation of diffusion coefficient with pressure. So, what you do is you try to plot this graph one by one. Let us say I have done it in Excel. So, you plot log D versus 1 over T. So, here this is 1 by T scale, and if you do a linear fit, you will get a slope, and this slope is nothing. So, the intercept is nothing but ln D0 is your intercept. So, from that you can get the value of D0, which in this case comes out to be 5.9 into 10 power minus 8 meter square per second, and the slope is equal to minus Q by R, and you can calculate Q using this relation, and it comes out to be 224.81 kilojoules per mole. So, remember to take the units correctly, and all should be consistent. The second part of the question concerns the pressure or pressure variation, because you know to find activation volume, and we are given to neglect the correlation effects. So, therefore, you can write delta V is equal to minus kBT into dou ln D by dou P at constant temperature. So, you basically again use any simple software to plot this graph and fit a straight line, and you will see that the slope that you calculate comes out to be this value, let us say, and here then you can plot it. So, after plotting you get the slope, and slope once you determine, you can multiply it with minus kBt. So, what you get is delta V. Now, delta V typically we represent in terms of atomic volume. So, in atomic volume you have the 4 by 3 pi r cube, r 166 picometer. The data was taken from the concerning the gold diffusion. So, therefore, I am using r equal to 166 picometer, which is atomic radius for gold, and therefore, the volume comes out to be 1.92 into 10 power minus 29 meter cubes. So, if you want to represent activation volume in terms of omega, the atomic volume, then you just simply divide it. So, you get the answer as 0.966 omega. So, with this we come to the end of the tutorial lecture today. Please do try out the problems, and if there are any concerns or doubts, you can put it in the forum. Thank you.